Okay, good morning, Saravanan. Okay, so I hope you learned some new things at last from last two sessions. So today is the interesting topic, carbon cycle. Now I request Dr. A. Nicholson to introduce the resource person.
Okay, welcome you all. Let me introduce the chief guest, Dr. Saravanan Ramasamy, Assistant Professor, Department of Chemistry and Biochemistry, Angelo State University, USA. So he did his Bachelor of Science in Chemistry, and PhD College of Arts and Science, Coimbatore. Then he did his Masters of Science in Chemistry in SRMV, College of Arts and Science, Coimbatore. And then he moved to University of Oklahoma. There he did his PhD in organic chemistry, and then he did his postdoctoral research in the same university, University of Oklahoma, Norman. And he has published more than 20 papers in international reputed journals. And now he's a member of core curriculum committee and departmental liaison of second year retention plan. And he's current member of American Chemical Society, ACS, and current member of Texas Academy of Science. Also ASU representative for Texas T&M Engineering Experiment Station. Okay. Once again, I welcome you all. Now the session is over to our chief guest, resource person.
Okay. Thanks for joining. Can you hear me?
Yeah, I'm here.
Okay, good.
Okay.
Thank you again for joining this webinar. Thanks for organizing. Thank you to National College of Engineering. Thanks to the department head, and thanks to Dr. Ramachandran, who contacted me last week. I think I hear some noise. I'm going to, let me see. Okay, that's good. So please mute your microphone because it's too much of noise here. The one disadvantage of giving webinar, too much of noises from every side. Okay, so so I'm sitting in Texas now. It's 11 o'clock Tuesday night. So I'm sitting in my office. It's going to be a midnight soon. And in the past 2 weeks, when I was contacted by Dr. Ramachandran to give this webinar, I was given two choices. One, to talk about the research, my research, and the next one is to give a science awareness talk. I chose the second one. So this is going to be a science awareness talk. It's not my research. I did not have any research background in this. And I always like to talk about the science. And it was the coronavirus time. And when everyone is scared about nature, I want to put some more oxygen into it, right? So I just want you to take this as a science awareness video. And I did not have any statistical chart or data to present. So let's talk. And like I said, it's going to be a midnight soon. I may not talk coherently. So how about we all watch a movie, right? So I'm going to show you a movie for next 20 minutes. And after that, we'll continue our talk. This is the first part of the seminar. The first part is a video that I created for you. I spent last 2 days in the lab making some video, making some experiments to show how the science work, how the carbon dioxide work, the properties of carbon dioxide. I compiled that into video. I just put it on the YouTube just half an hour back, and I'm going to show that video to you. It's a 20 minutes video. I hope I won't sleep. So why don't we watch the movie first, and then we'll come back to talk like this. Now, I want everyone to mute your microphone, but you can still use your speaker because the video has some audio in it. Okay, here we go. It's a science awareness video. I'm going to present the video right now. Let me know if you can't hear anything or can't see anything. Just let me know. I will give another option. Okay, now you see the screen. Okay, so the first part of the carbon cycle, right? Part 1. Carbon is one of my favorite elements in the periodic table. Carbon can make stable bonds in endless variety of organic molecules. That is the basis of life. Now, this is carbon dioxide. It's not a toxic gas. We'll talk about the properties of this gas in the first part of the webinar using simple lab experiments. The second part of the webinar will explain how the carbon cycle affects the global climate. Buckle up. This graph is the main reason why I do this webinar. Have you seen this before? What does this curve indicate? A, number of people affected by the coronavirus in the last 3 months. Or B, the amount of carbon dioxide in our atmosphere in last 300 years. If you said B, you're right. Carbon dioxide, the major greenhouse gas, is exceeding the limit that the Earth had maintained for the last 2 million years. And we are responsible for that. Before we talk about all of these, let's study some properties of the carbon dioxide. The gas that comes out of the flame is carbon dioxide. There is a fuel in the lighter, basically a hydrocarbon, butane, propane, or octane. They come from fossil fuel. The plants and animals died long back, and it took hundreds of millions of years to convert the organic matter into fossil fuel. That is oil, coal, or natural gas. See how I burned the million-year-old fossil fuel in just a fraction of a second and release the carbon dioxide into atmosphere. So next time when you light a gas or put petrol in your car, remember you're burning a dead dinosaur. This fuel in my hand could be a dead T-Rex. The hydrocarbon fuel in this lighter mixes with the oxygen in the atmosphere to form carbon dioxide, CO2. What happens to the hydrogen in the hydrocarbon fuel? The hydrogen combines with the oxygen to form water, H2O. That is the byproduct of this combustion reaction. Now, where is water? That's probably evaporated by the heat. So anytime you burn something, the products of the reaction are energy, water, and carbon dioxide. I am burning sugar right now while I speak. I inhale oxygen, and my body uses it to burn the sugar into energy, water, and carbon dioxide. The reaction is same. Here is another fuel, ethyl alcohol. This is not a fossil fuel, so don't worry about the dead dinosaur. Ethyl alcohol or ethanol is a plant-based fuel. I'm going to pour the 70% ethyl alcohol into this jug and give it a shake. And pour the extra fuel back into the flask. Now, I'm going to burn this. the product of the combustion reaction is still same. Energy, carbon dioxide, and water. Are you ready for the whoosh? That's that. Now let's see if I can collect the product, water. Okay, that's our water product. So we have the energy in the form of light and heat, we had carbon dioxide product, and we had the water product. Okay, here is vinegar. That's a dilute form of acetic acid inside the flask, right? And this is baking soda or sodium bicarbonate in the balloon. I'm going to mix these two. When you mix this acid and base, you would get carbon dioxide. This is not a combustion reaction, so the products are a little different. You would get carbon dioxide, water, and sodium acetate. Let's see. Okay, the carbon dioxide product is in the balloon. Water and sodium acetate are in the flask. I'm going to keep this carbon dioxide for a later use. Right. So let's put a clip on this. Let's keep this for a later use. Like water, carbon dioxide can exist in different phases: solid, liquid, and gas. But the temperature is a little tricky here. At the atmospheric pressure, you can convert the carbon dioxide gas into solid by cooling it down to negative 78.5 degrees centigrade. We're going to do that now. Let's take the solid carbon dioxide first, and then we'll discuss about the properties of that. So, inside this tank, we have a compressed carbon dioxide gas. The tank is kept at room temperature, so the carbon dioxide should be gas inside the tank. Now, when we release the carbon dioxide from the tank, it goes from a higher pressure suddenly into a lower pressure, that is the atmospheric pressure. That would also lower the temperature to below negative 78.5 degrees centigrade. That gives our solid carbon dioxide. I'm going to collect that in this box. Okay, ready for this? It would make a hissing noise and probably takes 5 minutes to fill the box with solid carbon dioxide. Okay, we got a little bit of solid carbon dioxide. The solid carbon dioxide is called dry ice because it does not form a liquid. When the temperature rises above negative 78.5 degrees centigrade, carbon dioxide goes from the solid phase directly into gas phase. The process is called sublimation. Camphor is a well-known compound that sublimates from solid into gas. We use carbon dioxide dry ice to preserve food, make ice cream, or create foggy scenes in the movies. In our next experiment, let's see how a gram of carbon dioxide turns into gas. Okay, this is about 22 grams. I'm going to put that into this flask and capture the gas into the balloon. Okay. I'm going to speed up the process by moving the solid carbon dioxide into a warm water bath. Okay, I'm going to take this gas, carbon dioxide, and clip it for later use. Now, we know that carbon dioxide sublimates from solid to gas skipping the liquid phase. Can you ever get liquid carbon dioxide? You can. You have to increase the pressure. Here's the phase diagram. At the atmospheric pressure, carbon dioxide is either a gas or a solid. To get a liquid carbon dioxide, you need to raise the pressure. Let's do it. In our next experiment here, we'll apply some pressure to get a liquid carbon dioxide. I put some dry ice into this tube. Okay, here's some dry ice in the tube. Seal the tube and drop it in the warm water. Now we can see the liquid carbon dioxide, right? It's inside the tube, right? The pressure and a little bit of temperature helps to convert the solid carbon dioxide into liquid carbon dioxide. The liquid carbon dioxide is a good solvent used for extraction purpose. Our next experiment is an extraction of limonene from lemon. Limonene is an essential oil you can find in lemons and in other citrus fruits like orange or grapefruits, mostly in the skin. So I'm going to peel the skin off from the lemon like this. Take the skin and put in the test tube, add some dry ice, that is solid carbon dioxide, tight seal, drop it in the warm water. The solid carbon dioxide will turn into liquid carbon dioxide that will act as a good solvent to extract the oil of lemon from the skin. Okay, here's the test tube with dry ice, lemon peel, filter paper. All of the solid carbon dioxide turned into liquid passed through the lemon peel and collected in the bottom. Now I can see a drop of limonene in the bottom. That's how much we can collect from this much of lemon peel. Limonene has a good lemon scent. We use that in room freshener or in other cleaning products. Carbon dioxide is a safe and an efficient solvent. We can use that many places, like extracting caffeine from coffee or tea to make a decaffeinated coffee or tea, or in dry cleaning to extract dirt from our clothes that are sensitive to water. Carbon dioxide gas is very commonly used as a fire extinguisher. Because carbon dioxide gas is denser than air, it will replace the less denser oxygen to put out the fire. This beaker has the regular atmospheric air, and in this beaker, I'm going to put the carbon dioxide gas we collected previously. Okay, atmospheric air. Now, in this beaker, I'm going to put the carbon dioxide we collected from the previous experiment. Now let's see how the carbon dioxide puts out the fire. See? Let's try one more time. Okay. Regular atmospheric air, carbon dioxide. Right? Carbon dioxide puts out the fire. Carbon dioxide is a denser gas. It fills in the bottom half of the beaker. To see more obviously, I'm going to add some solid carbon dioxide here. Okay, here's a tiny piece of solid carbon dioxide. Carbon dioxide is filled in the bottom part of the beaker, so when you go there, the fire is extinguished. Now, because carbon dioxide is a denser gas, you can pour it like a liquid. Let's try. Okay, there's a flame in the atmospheric air. It's good. Now, I'm going to pour the carbon dioxide into this beaker. So you transfer the gas, carbon dioxide, from one beaker into another beaker. Now, our next experiment is important. We're going to see the greenhouse effect of carbon dioxide. Carbon dioxide is a part of our atmosphere. It absorbs and traps the heat radiation from the Earth's surface. Because of the greenhouse effect of carbon dioxide, we have a nice and warm weather. Otherwise, Earth will be a frozen rock, thanks to carbon dioxide. But too much of carbon dioxide in the atmosphere will give a toasty, hot climate. There are two flasks here with equal amount of water. Consider the flask as our Earth and the water in the flask as our ocean. I'm going to fill the first flask with the regular atmospheric air and fill the second flask with the carbon dioxide gas we got from the previous experiment. Now, this is an example of our current atmosphere in 2020. This is an example of our future atmosphere with a lot of carbon dioxide. Here comes our sun. Now let's see how the temperature changes in each flask. After about 45 minutes, you can see the temperature in this flask with the regular atmospheric air is about 46 degrees centigrade, and the temperature in this flask with excess of carbon dioxide is about 50 or 51. So there is a difference of 5 degrees centigrade. The climate change and the higher temperature not only make us sweat more, but it also raises the sea level, and the coastal regions will be under the sea in the future. Our next experiment shows how the temperature increases the volume of water. We know that liquids expand when you heat. Thermometer is based on that principle. When the body temperature heats up the mercury or alcohol in the thermometer, we see the rising liquid by the scale. Water behaves the same way. Now this flask has 500 ml of water. I'm going to mark the water level. That's the initial water level. Now let's check the temperature. The initial temperature of the water is about 29 degrees centigrade. Now I'm going to apply some heat. This is a hot plate. Here's a dial. Raise the temperature. When you heat water, it would expand initially, and when the temperature reaches the boiling point, it would evaporate. Okay, after a few minutes of heating, now you can see the difference between the initial and the final volume. Okay, the temperature is about 45 degrees centigrade. It started from 29, and the final temperature is 45. From this, you can predict what would happen to the sea level when the global climate changes and the ocean temperature rises. Carbon dioxide emission not only increases the global temperature and sea level, it would also make the ocean more acidic. Carbon dioxide, like any other compound, can dissolve in water. The atmospheric CO2 can make it down. Okay, so everyone, please mute your microphone. It looks like there are too much noise coming from some of your device. I see some of your videos. If you could, you can turn off the videos so that the video from my side would be a little more clear. Thank you.
No, everything's okay, Saravanan.
Okay, thank you, Dr. Ramasamy.
Direct contact with the water on the ocean surface or through rain. When the water absorbs the atmospheric CO2, it makes carbonic acid in a reaction like this. Now, our next experiment is going to test how the carbon dioxide will change the pH of water. Okay, this is distilled water. The pH of distilled water is 6.98 or 7. Now, see what happens when it toss a piece of dry ice, that's pure carbon dioxide, into this distilled water. Look at the pH. It moves towards the acidic side. It's not toxic, like I said. You can put your finger in, just a carbon and water. Some of the CO2 escaped and some reacted with the water to form carbonic acid. And the pH is 4.55. This is carbon dioxide mixed with water, carbonated water, or simply soda. Now, the pH is 4.45. Let's try the pH of soda I bought from the market. The pH of Sprite is 3.7. Right? So that's a soda we made in the lab. That's a soda I bought in the market. They're both carbonated waters. Now this tells how ocean will be acidified when you emit a lot of CO2 into the atmosphere. Ocean acidification is so bad that it kills a lot of marine species. I may be exaggerating the pH of the ocean here, but the fact is the pH of the ocean has changed 0.15 towards the acidic side in last 50 years. Our next experiment will show how coral reefs and seashells will be affected by the ocean acidification. I'm going to throw one of these into the carbonated water and see how the weight changes. Let's take the weight of this seashell. It's 14.905 grams. Now I'm going to drop this into carbonated water. The seashell and coral reefs are made of calcium carbonate. When ocean absorbs a lot of carbon dioxide and forms carbonic acid, the acidic proton in the carbonic acid will convert this calcium carbonate into bicarbonate. That will make the shell fragile and thin, that will no longer support the life of the shell building organism. Coral reefs are the habitat for many other marine organisms. When it's destroyed, it puts a lot of other creatures into extinction. That would damage the major food chain in the ocean. Okay, after soaking this seashell in carbonated water of pH 4.45, the weight of the seashell is 14.83. So in just about 75 minutes in a carbonated water, the seashell has lost a weight of 0.08 grams.
Okay, so that's the end of the first part. I hope you learned something. If you're not a chemistry student, this might be a little bit new to you, but that's fine. Like I said, this is simple science I made for a general audience. What we learned is carbon dioxide is a part of our atmosphere. It's good because that gives the temperature. Carbon dioxide is the temperature adjusting gas, right? But at the same time, we can use the carbon dioxide in our real life. When you cook something, like when you bake a cake or a bread, you put sodium bicarbonate and acid in milk or other form. They react and gives the carbon dioxide, and that's how you get a fluffy bread. And we can also use the that's carbon dioxide gas. We can also use the carbon dioxide gas to fire extinguish, and we can use the liquid carbon dioxide or a supercritical carbon dioxide as a dry cleaning. When you go wash your clothes, give your clothes for dry cleaning, what they do is they put carbon dioxide on your clothes. It acts as a solvent as a liquid or a supercritical liquid and removes the dirt from your clothes, basically extraction. And solid carbon dioxide is used to preserve food or make ice cream. So these are the good side of carbon dioxide, and here is the bad side. Carbon dioxide gives higher temperature. If you increase the amount of carbon dioxide in the atmosphere, it will increase the temperature. When the temperature increases, it will increase the water level in the ocean. So most of the coastal regions will be under the sea. It also acidifies the ocean. When the ocean gets acidified, the marine organisms will die. Mostly the shell building organisms will die. When they die, the food chain will be broken. That's a lesson we learned from the video. Now, I'm going to connect this to the global climate. I don't have good slides to show you. Like I said, this is just an awareness talk, not about my research, no statistical data. So I'm going to talk like this. So you're going to see me and listen. Good? Okay. Okay. So how did we get the carbon dioxide in our atmosphere in the first place? Who put the carbon dioxide? Give it a thought. Where do you think the carbon dioxide come from? Carbon dioxide, like any other inorganic molecules, it formed billions of years before. When the Earth was formed and settled down in a spherical shape, the inorganic molecules were stored in several reservoirs like lithosphere, hydrosphere, or atmosphere, or in plain English, it's simply land, water, and air. So there are a lot of carbon dioxide. There were, in billions of years before, a lot of carbon dioxide in land, water, and air. And we know that molecules don't stay in one form. They tend to change. That is, they want the stability. Any chemical reaction will look for stability, right? That's the principle, right? Stability is the driving force for all chemical reaction, no exception. Molecules will react to energy, pressure, concentration, and exposure to other molecules. That's simple reactions, right? When you put pressure, give energy, give concentration, give another molecule to react with, a molecule will react and the atoms will change from one form into another form called chemical reaction, right? That never stops. Molecules never stop. It's an endless cycle of atoms moving from one molecule to another molecule to another molecule to another molecule. They never die. You and I are made of organic molecules. When we die, right, the molecules change from one form into another form. It takes a new life. There is no death for those particles. The RIP is only for our soul, not for our body. This body will be recycled into the nature. It goes into a different life, like a plant, or it could become my carbon atoms in my body will become a part of a different animal, different plant in the future. Let me check if the video is okay. Is everyone hearing okay? Okay, let me know if you can hear anything. Okay, so let me go back to the topic. Carbon is one of these atoms that travel between molecules through chemical reactions. Carbon takes many forms in the cycle, right? A few billion years back, when there's no life on the planet, carbon was stored in carbon dioxide, carbonate, and methane, mostly the organic and the inorganic molecules, no life. But carbon dioxide, the most oxidized form of carbon, is a magical compound that is responsible for both the birth of life on Earth and mass extinction on Earth, right? Carbon dioxide is responsible for the life and death of many animals, right? Earth has been through several of this mass extinction. In almost all cases, carbon dioxide level in the atmosphere is the major reason. What do you think is the normal percentage of carbon dioxide in the atmosphere? Right? When you look at the atmosphere, how much carbon dioxide do you think is in the atmosphere? Take a guess. Right? I give some choices. You don't have to answer me, but think in your mind. A, 40%. Right? How much carbon dioxide is in the atmosphere? A, 40%, B, 4%, C, 0.4, D, 0.04%. How much carbon dioxide is in the atmosphere? Okay. If you said D, 0.04, you're right. The percentage of carbon dioxide in our atmosphere is only 0.04, not 0.4, not 4. But this is a very small number compared to the oxygen and nitrogen. It's a very small number. But if there is a small swing in the number, that will throw all of us into the ocean, right? Carbon dioxide absorb the infrared radiation from the Earth, right? When sunlight falls on the Earth absorbs the heat and it radiates back into the space. Most of the heat will be radiated back into the space, but some of them will be absorbed by compounds like carbon dioxide, methane, water, right? So that's the only energy we get from outside the sun. Sorry, from outside the Earth. Sunlight is the only energy we get, and we don't want to keep too much of that. We don't want to heat up our planet. We want to emit back into the space, but carbon dioxide, that's the opposite. It keeps the light. It keeps the heat energy. Okay, some of the heat will be absorbed by the ocean. Some will be absorbed by the land and surface and the objects, right? All of the heat from the sunlight will be absorbed by these objects. What happens to that energy when they absorb? A particle absorbs the energy. What do you think will happen to that heat? It should go somewhere, right? Let's say you park your bike or car outside in the sunlight. It gets hot. In the evening, after the sunset, it cools down, right? Where did the heat go? In the daytime, your bike was too hot. In the nighttime, it was cool. Where did you think the heat go? It probably went to the atmosphere, right? The particles in the atmosphere absorb the heat. One of that is carbon dioxide. Right. So our atmosphere is mostly made of nitrogen and oxygen. Nitrogen is 72% in the atmosphere, and oxygen is 21%. That's total 99% of oxygen and nitrogen. The remaining 1% has all of the other gases like argon, neon, carbon dioxide, methane, water vapor, sulfur dioxide. All of these are just 1%. Carbon dioxide, methane, and water vapor, right? These are the potential heat trapping gases, also known as greenhouse gases. Methane is flammable, natural gas. When it's released, it probably catches fire. If you see the oil plant, they pull out the oil, and you always see a fire going on from their chimney. It's because they don't want to release the methane. When the methane is released, it's a very potential greenhouse gas. So what they do is they intentionally burn the methane and releases carbon dioxide, which is a little less greenhouse gas, less potential greenhouse gas. So there is a way to cut off the methane from going into the atmosphere. Number two, water vapor. Water vapor is another heat-trapping compound, another greenhouse gas, but nature has the own way of controlling the water vapor in the atmosphere. What do you think will happen to the water vapor. If you put too much of water vapor in the atmosphere, what happens? You get rain, right? So when there's too much of heat, the ocean evaporates into water vapor. Water vapor goes into the atmosphere, and it becomes rain. So there is a way of controlling water vapor. Nature has its own way. There is a way of controlling methane. We have a method to control release of methane, but there is no way to control the release of carbon dioxide, period. So nature can only hold enough of carbon dioxide. If you put too much, it will stay there forever and absorb the heat and give a toasty, hot climate. CO2 cannot be converted into rain. Have you ever seen carbon dioxide changing into liquid and falling as a rain? No, right? We just saw in the experiment, in the video, to get a liquid carbon dioxide, you have to put a lot of pressure. I put a dry ice, tight seal, and heat. That's how I get the liquid carbon dioxide. There is no way you can get liquid carbon dioxide in a nature process. So liquid carbon dioxide, sorry, the CO2 in the atmosphere cannot fall as a rain. To make a liquid CO2, we need pressure. Okay, CO2 cannot be converted into solid at the room temperature. You have to give, or you have to take out the energy from the CO2. You have to take out negative 78.5 centigrade below the zero to get solid. There is no way to convert the gas CO2 into liquid. There is no way to convert the gas CO2 into solid. The CO2 that you put when you fire, when you burn gas, when you drive your bike, when you drive your car, when you smoke, or when you put your light bulb on, every time you burn something, you're putting a lot of carbon dioxide. It goes into the atmosphere. It stays there forever, hundreds of thousands of years. It cannot go anywhere, right? It absorbs the infrared light from the Earth and the other object and keeps the heat energy. The regular amount of carbon dioxide is good. Like I said before, it keeps us warm. But if you put too much of carbon dioxide, Earth will be like Venus. No life on Venus. It's like a toasty climate. Everything is hot, 100 C. So too much of carbon dioxide gives boiling temperature. Too little carbon dioxide will give a very cold temperature, like a negative 50 C. CO2 in the atmosphere is a thermostat that we have in our AC. You can adjust the level of CO2 in the atmosphere to make the climate cool or to make the climate hot, right? Now there are two cycles of carbon dioxide. And that's the topic of this webinar, the carbon cycle. Right? To circulate this carbon dioxide from the atmosphere, there are only two ways. One is long-term, another one is short-term. The long-term carbon cycle takes millions of years to circulate the carbon. It starts from the volcano. Right? Volcanoes burn the sediments from under the ground and emit the carbon dioxide into the atmosphere. That's the starting point of how we get carbon dioxide. I asked a question in the beginning, how did you get carbon dioxide? Most of the carbon dioxide are converted or come from Earth through the volcano into the atmosphere, right? There are many rocks and fossil melted deep underground. When there's an excess of pressure, all of them will come out in a volcanic activity. And we know when you burn something, you get carbon dioxide. A prolonged, continuous volcano activity for hundreds of thousands of years in the history, in millions of years before, there was a volcano. There were many volcanoes that burned continuously for hundreds of thousands of years, put a lot of carbon dioxide in there. And we know what happens. The atmosphere gets hotter, right? And the Earth will be very hot There'll be no life on Earth. This will put all of the life on Earth in danger. A hot climate kills millions of animals. It happened in the history. If you go back to the geological record, you can see many mass extinction happened because of the increase in carbon dioxide. Right. Then, okay, that's the starting part of climate. Okay, can you hear me now? Is everything okay?
Yes, it's okay, sir.
Okay, good. So now the carbon dioxide come from land to the atmosphere. It takes millions of years by the plants and the ocean to absorb the carbon dioxide. Right? The atmospheric carbon dioxide will go to the ocean, absorbed by the ocean or the plants. And it's a very slow cycle. It takes, like I said, hundreds of millions of years to cool down the temperature that was raised by volcanoes. Throughout those millions of years, there is no life on Earth. And then now, after a few 100 million years, enough carbon dioxide will be absorbed by the ocean and plants, and the atmosphere gets cool. When the atmosphere is cool, the life will come back. And when the life come back, like plants and animals are there, like big trees, dinosaurs are on there, then a sudden geological event like flood, tectonic movement, soil erosion will kill those animals, put them under the sea, and it will go under the ground, convert them to fossil, right? Our Earth lithosphere underground is like a pressure cooker. It applies a lot of pressure and heat to cook the dead plants and animals to turn them into fossil first, and then fossil fuels. What are the fossil fuels? Coal, oil, natural gas. So once it was a tree, it was a dinosaur, now it's dead, and it became coal, oil, or natural gas. Again, it takes hundreds of millions of years to do that. Atmospheric CO2 will be removed from the atmosphere and stored as fuel, as fossil fuel, under the ground. Right? When so much of carbon dioxide was removed from the atmosphere, what happens? When there is no carbon dioxide in the atmosphere, what happens? Climate becomes cool, right? That is the beginning of Ice Age. Once it was boiling temperature, now millions of years, plants and ocean absorb the carbon dioxide stored underground. Now it's Ice Age. The temperature is below 50. The Ice Age will last for hundreds of thousands of years. Most of the animals and plants will die. This is another mass extinction. So both the hot climate and the cool climate will kill life on Earth. And suddenly, one day, volcano will erupt, burn all the sediment and fuel back into the atmosphere. The cycle begins. Volcano gives carbon dioxide, ocean and plant absorb carbon dioxide, store it under the ground as fuel. Volcano puts that back in the atmosphere. That is the long-term cycle. It takes millions of years to do that. Okay, in the recent geological past, like last 50 million years, there was no major volcano. No major volcanoes in last 50 years. The carbon dioxide level have been gradually dropping to around 300 parts per million when the climate is cool, with some ups and downs. Now, we are there in last 2 million years. That's called the interglacial period, the period between two ice ages, right? A little bit warm temperature, not too much of ice, not too much of hot climate. We are very lucky to be in this part of the, in this time of the history. Okay, this pleasant weather that we are experiencing now, right? What is the room temperature? 30 C? Maybe in Tamil Nadu, it could be 40 C today. This pleasant weather will be there for another millions of years. It should be there. It should be like for next 50 million years, we don't have to worry about it until we, Homo sapiens, put a lot of carbon dioxide into the atmosphere, right? There will be another major climate change. So this is a long-term cycle. The first one of the two cycles. Long-term cycle puts a lot of carbon dioxide in the atmosphere. From the atmosphere, it goes to the hydrosphere, that is the ocean. From the ocean, it goes to the lithosphere, that is a land, and it cycles in a time frame of hundreds of millions of years. The second cycle is short-term cycle. That's very productive cycle because it goes through biosphere. What's biosphere? Us. Life. Life is biosphere, which is relatively fast. This carbon cycle is relatively fast and relatively productive because it goes through my body to the ground, to the microorganism, and to the plant, and to another animal until I eat it, right? So this short-term cycle is measured in a lifespan of an animal or a plant. It's largely connected to the food chain on Earth. Like plants take the carbon dioxide from atmosphere. We all know that. We breathe? We breathe oxygen. Plants breathe carbon dioxide. So plants take the carbon dioxide from the atmosphere, take the water from the ground, nutrients from the ground, and energy from the sunlight. That's the only source of energy plants can get. It takes the sunlight and build its food. Plant build food from the carbon and water and nutrition. Like I said before, sunlight is the only source of energy. There is no other go. Whatever we spend, like I speak, when you walk, or the energy you spend in the light bulb, in industries, in car engines, all of that energy comes from sun. No other way. So each one of us have a little sun inside us. How is it possible? Plants use sunlight to prepare food, right? It takes light, photosynthesize. The energy in the light is converted into covalent bond. If you're a chemistry student, you know what's a covalent bond. It takes light to make a covalent bond in carbohydrates, aka sugar, right? Also known as sugar. This very process is the foundation of the fast carbon cycle, or the biological carbon cycle. That's the start of the slow, the short-term cycle. Okay, once the carbon dioxide is converted into carbohydrate, what's carbohydrate? Sugar, glucose, fructose, maltose, they are carbohydrates. Plant make them from the sunlight, only energy plant can get. And then the inorganic carbon dioxide from the atmosphere is now converted into an organic molecule. Sugar, carbohydrates are organic. Carbon dioxide is inorganic. The energy from the sunlight is now stored in covalent bond in these molecules. Now, what happens to the carbohydrate in the plant? What do you think will happen to the carbohydrate in the plant when the energy is converted into covalent bond in the carbohydrate? What happens to the energy? We eat it. Animals eat the plant. The energy and the carbon goes with that into the body of the animal. Then the animal, including human being, burn carbohydrate. While I speak, while I walk, I burn carbohydrate, release it back into the atmosphere. It started from the atmosphere, right? It went to plant. I ate the plant and I released carbon dioxide. It's a very short cycle. The remaining organic matter that I cannot burn, I ate food, I cannot burn all of it, then it will be excreted and goes back to the ground. It's another food chain. Now, this food chain goes on if a herbivorous eat the plant, like a cow, goat, deer, they all eat plant. They will be eaten by carnivores, tiger, lion, human beings. And then it goes on. The carbon moves from one molecule to another molecule, one body to another body. Like I said, there is no death to atoms or molecules. It's only death to our soul. My body will be regenerated, put back into the cycle. Carbons in my body will go back into the cycle. It's nature, right? When plants and animals die, what happens to dead bodies? When plant dead is died, what happened? It will be decomposed by the microorganisms, the bacteria. Microorganisms eat the organic matter, spend energy, and exhale carbon dioxide. Again, carbon dioxide goes to atmosphere. The dead animal, even the dead animal is eaten by the microorganism. Carbon dioxide is released by the microorganism into the atmosphere. So microbes, microorganisms are the recycling unit of Earth. They recycle the dead bodies. They eat the dead bodies and put them back in the cycle. So don't kill microorganisms. They're good. If the dead animal is burned instead, if I was not decomposed, I will be burned. When I was burned, again the carbon dioxide goes to the atmosphere. It's a cycle, right? Carbon dioxide will there is no waste in this cycle. In each case, carbon dioxide will be oxidized. Carbon will be oxidized to carbon dioxide. Oxygen will be combined with the carbon and put it back into the atmosphere. And even in the forest fire, when you burn, when Amazon was on fire, we started with that, like 2020. This year is very bad. We started with the forest fire in Amazon, and then there was some hurricane, and then Corona. It goes on. So when forest fire happens, the carbohydrates, the plants will be burned, oxygen will be released, oxygen will be taken by the fire, release carbon dioxide. Cycle goes on. And this carbon dioxide, this short cycle, the amount of carbon dioxide in the short cycle is very little, not too much compared to the previous cycle. And during the winter in the atom, when the plants are dead, there will be no carbon dioxide absorption, right? So in the atmosphere, there will be a lot of carbon dioxide. There is no plant to absorb the carbon dioxide. Atmosphere will be a lot of carbon dioxide. Then when the spring and summer comes, plants will grow, take the carbon dioxide, it lowers the amount. It goes like that. Good. I think we're running out of time. Let me go to the next process. Okay, so we know the two cycles, the longer cycle and the shorter cycle. The shorter cycle is very productive. It goes through the biological system. Now, let's see how the human beings intervene and kill the two cycles. We are the most evolved species on Earth. We are here for last 2 million years. Last 2 million years. That is like 2 seconds of a day. If you consider the history of Earth, the time of Earth into 24 hours, human beings are alive only in the last 2 seconds. Or if you consider the number of species, number of lives that lived through the history, we are a very small population. Human beings are a very small population. Like if you convert the number of animals into a dictionary, we are not even the last word on the last page. We are the period that comes after the last word of the last page of the dictionary. There were billions and billions of animals lived through the history. We are the last one. Like dinosaur lived for 200 million years. We are only here for 2 million years. Right? So throughout the history, these other animals, other than human beings, they lived perfect life, clean life, no carbon print. They obeyed the rule of nature. They did not do any waste. They did not kill this cycle. They helped support the life of other animals. But the way we live, human beings live in last few centuries, not the previous year, in the last few centuries, we broke the chain carbon cycle at every single transition. It is how we damage the short-term cycle, the productive one. Number one, we cut the forest and never planted enough trees. So there is not enough plant to absorb the carbon dioxide from the atmosphere, break in chain. Less tree is equal to less food for animal and more carbon dioxide in the atmosphere. Then we stock the limited food in our market. We put a fence in our farms so the other animals cannot take the carbohydrates. We use pesticide so the microorganisms or the pest cannot eat those trees and plants, another break in a food chain. And then we waste a lot of trees by making furniture. Here's a table, here's a chair. These are made of wood. It's supposed to go to the ground. It's supposed to be decomposed by the microorganism and should go to the ground, but we stop the cycle by making furniture. The dead trees, they are the food for microorganisms. Now they are starving. They don't have food. Okay, now look at that. We make plastic out of carbon. They never decompose. Without those dead plants, without those carbons, the animals will lack carbon. And we trash the plastic that is uneatable carbon structure into the ocean that kills the fish. So every time we manufacture a lifeless thing like headphone, mouse, every time you make something, you're stealing the carbon from the carbon chain and storing it here, storing it in this for hundreds of years. They never go back to the cycle, break in the cycle. Look around the stuff in your house, look around your stuff and see how many stuff are made of carbons. They will not decompose for hundreds of years. That itself is a mass extinction, right? We are killing so many animals by making non-living organisms. By manufacturing lifeless things, we kill lives, right? By one way or another, we stop the chain. And now let's look at the more dangerous behaviors of ours. This is how we put a big hole in the long term or a powerful cycle. We dig fossil fuel like coal, oil, or natural gas and burn them into carbon dioxide. They're supposed to sleep under the ground for another millions of years, right? Until another volcano come. Now, we are replicating what volcano do. Our industries, our house, our car, our cell phone, they're all mini volcano, right? Because the energy comes from the cell phone through the charger is originally from fossil fuel, from coal, oil, from thermal power plant, right? When you drive a car, it comes from the oil. So what the volcano do is now replaced by the human beings. We are doing the same. And every second, we convert thousands of tons of fossil fuel into carbon dioxide throughout the year, throughout the world nonstop. Okay, let's compare this. We release 185 times, right? 185 times more carbon dioxide than a volcano do. In 2018, volcano released only 1% of carbon dioxide compared to what we human beings released. We released the 99%. Volcano released only 1%. So we live in the Anthropocene era. It's a new word, Anthropocene era, which means human being impact is more than the natural process of adjusting global climate. We exceed volcanoes. Our emission of carbon dioxide exceed volcano, and it's a record high, 400 ppm, 400 parts per million, which means if you take a handful of gas from the atmosphere and count the number of carbon dioxide, out of 1,400,000 them of carbon dioxide, which is very high compared to what we have in 100 years back. So the Earth had never seen this much carbon dioxide in 2 million years. Most of that are released in last 75 years after the Industrial Revolution, after the Second World War, when German is dropped, and we put a lot of our focus on industry, how to make stuff, and that released the carbon dioxide. In last 75 years, the curve was like this, like 2 million years before, and in last 75 years, it goes like that, right? So this has increased the average temperature of our globe to 1 degree Celsius in last 50 years. In 1950, the average temperature was 1 degree less. This is a planetary scale. Whatever I do, whatever I burn, whatever materials I use, that affects the planet. The planetary scale behavior of ours, right, changes the life on Earth. So we are in the middle of 6th mass extinction. I'm not making this up. That's true. We are in the middle of 6th mass extinction. The only difference is the previous 5 mass extinction was made by the nature, and the 6th one, this one, is made by humans. Okay. So human emission of carbon dioxide increases through century. We have not seen this tens of millions of years, and the climate has changed significantly. You know what happens to the ocean? The ocean absorbs that carbon dioxide, and the temperature will rise. Here's the prediction. The Paris Agreement, it happened in 2016. Most of the countries met in Paris, France, and they signed an agreement that they will reduce the carbon dioxide emission so that in next 100 years, right, the temperature will only rise 1.5 degrees centigrade. So that's the agreement, but we are not following it. We are going very fast. The 1.5 degrees Celsius rise will happen by 2035. Right? The temperature will rise 1.5 degrees by 2035. And the excess of carbon dioxide makes the sea level rise. When the sea level rise, there will be a dramatic climate change, flood, and then soil erosion, everything happen. And there will be climigration. A new word, climigration, means, you know, in COVID, everyone watches news channel. People migrate from Tamil Nadu to Bihar, Tamil Nadu to UP. They were walking. They are migrating. Why are they migrating? Because they don't have resource in this state. They're moving to a different state. There is a COVID, no life, no job. It happens in the future, not because of a virus, because of the climate. People in the major city will move out of the city to get water, to get to avoid the flood, to avoid the drought. Right? So by 2050, what's the world population now? 7 billion, right? By 2050, in 30 years, the population will rise to 10 billion. That is the most population it can reach. When my son, he's 4-year-old now, when my son grow up and go to the college, the population will be 10 billion. No enough food, very hot temperature, and then the population decreases to 4 billion. By 2100, the human population will be 4 billion. If we keep emitting the carbon dioxide, there will be too much of heat, mass extinction. By 2100 or 2100, the human population will be half. Okay, so finishing up, we need a stronger commitment from the government, from every individual, to cut down the emission of carbon dioxide. We need a zero emission, right? As an engineer, I think most of you are engineer, National Engineering College, Kovilpati. Most of you are engineer in there. You're still in the first year, second year, or third year. You're still going to choose your career. Choose this career. Choose a career to cut down the emission of carbon dioxide. Try to find something that is more sustainable, like a wind energy, tidal energy, or solar energy, put your focus on that. That's not enough. We need to move towards negative emission. We know what's zero emission, don't emit anything. What's negative emission? You have to put the carbon dioxide from the atmosphere into the ground. So think about that technology when you graduate out of National Engineering College. You need to think about your career to cut down your carbon dioxide, right? So one way to achieve this negative carbon dioxide is capture the carbon dioxide and put into the ground. So final statement. We need to make this commitment, and climate change should motivate the electoral decision. When you go to vote in the next election or in your municipal election, somewhere in your college election, you should think about pushing the climate agenda in politics. So whoever gives you agenda, see if they point out anything that is related to climate. Every local and regional authorities should make climate conscious choices. Climate change will affect everyone, even me and you. So every individual has to make this decision. We don't have to wait for the government. You as an individual can make choice. You can switch from the plastic bag, the one-use plastic bag, into a cloth shopping bag. You can do it, right? Last week we had an environmental day, and we also in the 50th year of Earth Day. So make it as a resolution. Don't use plastic bags. Use the cloth bag. You can do it. Don't use the use and throw water bottle. Use a good water bottle like this. We can use it for 1,000 times. You can save thousands of one-use plastic bottles by this. We know how to make choices, right? We have made good choices before. Very recently, it only took few weeks to educate and spread awareness about the coronavirus. It started from the March, April, May, June. In last 3 months, the awareness about the coronavirus is so widespread. Everyone knows about coronavirus. What's the shape of coronavirus? What's inside the RNA? Everyone knows that. In a very short time, we can change our habit. We practiced hygiene. We maintained social distance. We stayed at home for weeks. We did not go to job. So it's an extreme. You don't have to go for that extreme. Make simple choices like don't use plastic bag, right? So take this coronavirus period as a model to apply that to your climate change. You know how to flatten the curve. When the curve grows, flatten the curve, right? You know how to flatten the curve. So what is your climate action? What are you going to do? Thank you.
So thank you so much, sir. So this is Anuraj from National Engineering College, Kovilpatti. So it was very wonderful lecture, and we know about carbon and carbon dioxide from long time as a chemistry students. So, but we have never seen so what are the different cycles and how it is recycled in the earth, and how it is converted into different forms, how it affects, and a negative part and positive part, everything you have explained very well for us. And it would have been a wonderful experience for our audience also, I hope. So now the session is open for discussion. So if anybody want to interact with our professor, you can interact now. Now the session is open. Yeah.
Okay, so if you want to ask a question, two ways. You can type in the chat window, so I can read and give feedback, or you can use a microphone to talk one at a time. Don't 10 of you talk at a time. Okay, so I'm sorry about the video. It was made last minute. I just recorded the video yesterday and edit the video today and put it on the YouTube. So there was some jump cut. The audio was not clear. I will send the link to the video, the science video, soon, maybe in a couple of days. I'll send it to the organizer, and you can get it from them. Any question for me?
Saravanan, one participants are asked a question. You may read in chat box.
It's a long chat. I did not miss.
Go down.
Can you read that for me?
May animals cause increase in carbon dioxide levels, sir?
May animal what?
May animals cause increase in carbon dioxide level?
No. So animals are very short. They're breathing out carbon dioxide. I breathe carbon dioxide. I'm an animal. I breathe carbon dioxide, right? So that's a very less amount, this much, right, compared to what we emit. This emitting carbon dioxide is good. I emit carbon dioxide, and that is how the atmosphere get the carbon dioxide. The plant absorb the carbon dioxide. It's a very good cycle. Animals increase carbon dioxide, yes, but that's good. That's a productive cycle. I'm giving the carbon dioxide to plant, good. But whatever you emit through your burning car, bike, cell phone, the thermal plant, industries, that's the bad one. Okay, next question. Okay, I can't understand that. It's good that the kids watching the webinar. That's good.
Yeah. Is there any correlation between the corona and our carbon cycle?
No. The corona did not do anything directly to the carbon cycle. The only thing we did is we stopped going out. We stayed at home, so we did not burn enough gas. That lowered the carbon dioxide very little. Just a few weeks of not going out decreased the carbon dioxide to a small amount, but the overall change in carbon dioxide, it takes a long time to do it. We have to stop everything to put the carbon dioxide under control. But I'm not saying don't use cell phone, don't use energy. We are used to that. We are used to living this lifestyle. I can't live without the light, but get the energy from a sustainable source like a solar, wind, or tidal power. Don't take it from the fossil fuel. Don't wake up the dead dinosaurs. Next question. Thank you.
Thank you. Saravanan, India is a country. We have around 130 crore people. To give energy to such a population, I don't think so. No, the energy get from the solar or wind energy will be sufficient.
That's true.
So, yeah, we have to focus on the fossil fuel. No other go for our country, it seems. So that's the reason we are burning more coal, and we are generating power through thermal power stations.
Okay, that's true. So India is the second populated country. China, India, and America, United States. But who's using most of the energy? Not China, not India. United States is burning a lot of coal and gas, right? So because, like you said, we have 1.3 billion or 130 crore people, we don't have sufficient way of giving energy. We started that way. We started a wrong way of getting energy. I don't know who invented coal and gas and natural oil when there's a lot of energy from the sun. So we did not invent the way of converting solar into energy. That's the reason. That is why I suggest, and every other scientist suggests,
correct.
flatten the curve. Why did we flatten the curve in the corona? Staying at home, will it stop the corona? It never stops corona. We stayed at home because we give enough time to the doctors, to the nurse, to to the scientist to invent a new technology to stop the corona. That's what we have to do. We have to lower emission, give a time to the scientist, to the engineers, you, to invent a new technology. Right? So just give it time. You don't have to completely go away from the coal, oil, or natural gas. Slow it down, flatten the curve. Someone will invent the new way of getting the energy. It's there. Solar energy is there. It's not efficient. It's not economic. The windmill, it's popular now. It's not economic, but when all of us focus into it, it will become economic and efficient.
Thanks, Arvind.
Thank you.
Dr. Saravanan, there is also one more audience asked some questions. We are saying reduce carbon dioxide level, but is that we can live without CO2?
No, without CO2 we can't. If there is no CO2 in the atmosphere, heat from the sunlight touches the surface, goes back. The Earth will be negative 50 degrees centigrade. We can't live. We are not used to that. So we need carbon dioxide in the atmosphere. We need 0.04% of carbon dioxide. Don't go above that. Keep that. I think it's a 400 parts per million, 300 to 400 parts per million. That's how much we need. More than that is not good. Less than that is not good. That exact range, somewhere between 250, I think 250 to 400 is what we want, parts per million. That's how much carbon dioxide we want.
Thank you, Saravanan.
Mm-hmm.
Okay, as there is no more questions, I can conclude this session by saying a vote of thanks. So, on behalf of National Engineering College and on behalf of the organizer of this program, I thank you very much to that resource person, Dr. Saravanan Ramasamy, for giving a nice lecture on the carbon dioxide cycle. And also he explained everything through small experiments. Okay, it was very new experience to that audience. So I thank you so much, sir. Thanks for giving this lecture. And also I thank the participants. More than 120 participants attended this webinar through. So I thanks all the audience for their patience and enthusiasm towards this webinar. And also I am happy to announce that we are conducting this webinar series. So tomorrow also we will have one webinar on the topic role of engineer in drug design. So as this is engineering college, most of the engineering students will be the participants. So we have planned this talk. So role of engineer in the drug design. It will be delivered by Dr. Harish Babu. He is right now in Japan doing postdoctoral research. So I hope this audience who attended today definitely will attend the tomorrow lecture also. I welcome all of you for the tomorrow lecture. Okay. So with this few words, I express my sincere thanks to the resource person as well as the all participants. Thank you, one and all. Thank you.
Thank you so much. So thanks for hosting me. Like I said, I send the video soon to the organizer. Thank you to the National Engineering College, Department of Science and Humanities, the head of the department, and Dr. Ramachandran for contacting me. And good luck, good day. Be a good engineer. Don't waste energy. Bye.
Thank you, Saravana.